Okay, so in today's video we're going to be looking at the differentiation of logarithmic functions. And in the same way that when we differentiate exponential functions, we only develop a rule for differentiating e to the power of x. In terms of when we differentiate log functions, we only consider a rule for differentiating log base e of x. We will in a later example, like we did in the previous video for differentiation of exponentials, we will look at how it is possible to differentiate a log with a base other than e, but essentially in the same way that we did with the exponentials, it requires us to manipulate the function to change its base to have a base of e, so that we can then differentiate it. Okay, so again we want to think a bit intuitively about what's happening with the gradient of a log function. So if we were to draw a rough sketch of the gradient function. So what is clear from the log function is that the gradient is always positive. So therefore when we draw the derivative function, it is always going to be above the x-axis. It's also clear that the gradient starts out very, very steep. Obviously nothing exists back here, okay? So the derivative function only exists where the original function exists. The log function is differentiable for x is an element of r plus, and so therefore our derivative function will only exist where x is an element of r plus. We can see when x is a very, very small number, the smaller it is, the steeper the graph is. Okay, so the gradient gets bigger and bigger and bigger and bigger the closer we get to 0. So we're going to have an asymptote in our derivative function. Okay, our graph is going to have some sort of asymptote happening here. And then we can see that as x gets bigger, the gradient remains always positive, but it gets smaller and smaller and smaller. So we're essentially going to have something that asymptotes here and asymptotes here. It's going to look something like that. So if we think about functions that we know that do that, maybe a truncus, maybe a hyperbola, so we might posit that maybe it's something like 1 on x. Now we're purely just guessing here based on the shape. It could be 1 on x squared, it could be 1 on x cubed, it could be 2 on x, it could be, okay, so it's not really clear. We're just thinking about the shape and what's happening and what maybe it might be. Okay, so let's have a look at a way that we can prove this using what we know about our derivative of e to the power of x. Okay, so this is quite a simple proof. You should certainly be able to follow this. No derivatives by first principles required here. So if we let y equal log e of x, and then we convert that to an exponential equation. So that's the same as saying that e to the y is equal to x. Okay. So then, I might write that the other way around actually. So let's say x is equal to e to the y. Then we want to differentiate both sides of the equation with respect to y. So the derivative of x with respect to y is dx dy. And the derivative of e to the y with respect to y is e to the y. We learned how to differentiate exponentials in the previous video. Okay, so then we're going to substitute for e to the y. Okay, so what we know is e to the y is equal to x. So that means we know that dx dy is just equal to x. And then if we take the reciprocal of both sides of this equation, we learn that dy dx is equal to 1 over x. And so the derivative of the log is indeed the hyperbola, but only where x is an element of r plus, so only half of the hyperbola. Now it becomes important when we get onto anti-differentiating 1 on x down the track. We need to be a bit careful around domain. Okay, we've already discussed the domain of r plus previously. Alright, so again, let's use our rule for the derivative of log e of x, derivative of log e of x being 1 on x, along with the chain rule in order to establish the following. Okay, so let's think about this. Now, I might do this first one the long way around so you can sort of see what's happening. Otherwise, it sort of might be a little hard to follow. So if we're going to use the chain rule the long way around, we let u be our inside function, which in this case is a, makes it u equal to ax. And that means that we get y equals log e of u in making that substitution. And then we can differentiate each of those. Oops, sorry, not dy, du. Dx, derivative of u with respect to x is just going to be a, and dy dx, derivative of, not dy dx, dy du, differentiating y with respect to u, derivative of log e of u is just 1 on u. And so we know then that dy dx, and 1 on u obviously is 1 on ax. So dy dx is going to be dy du times du dx, that's our chain rule. And so that is 1 on ax multiplied by a. A on ax, 1 on x. So what we actually see here is that the derivative of log e of ax is just the same as the derivative of log e of x. And that's because if we think about, if we have y equals log e of ax, our log laws mean that that's the same as log e of x plus log e of a. Okay, and that's just a number. Right, so derivative of, if we were differentiating that, derivative of log e of x is 1 on x, and derivative of a number is 0. So actually this a in here doesn't change anything. And that's because graphically what's happening, if we think about this function being written in this way, graphically this is just the graph of log e of x translated up by a number. And so therefore you're not changing the gradient at all. When x equals 5, the gradient of log e of x is the gradient of log e, is the same as the gradient of log e of x plus a number. It's just moved up higher. It's still got the same gradient at that point. So this is a really interesting point about derivatives of logs. So log e of ax is just 1 on x, because it is, thinking about the chain rule, 1 on ax multiplied by a, which is the derivative of the inside. And so you just get 1 on x. Where we need to be careful is in this next one. Because if we were to, I'll do this one the long way around as well. If we were to let u equal ax plus b here, du dx is a. If u is ax plus b, that means that y is log e of u. And dy du is 1 on u, which is 1 on ax plus b. Now the difference here is dy dx is, we know, dy du multiplied by du dx, and so in this instance that is 1 on ax plus b multiplied by a, and so it is a on ax plus b. Now in this instance those a's don't cancel. Okay, that's not how fractions work. We can't divide, you'd need to be able to divide the whole denominator by a, and a doesn't go into b. So it's not going to just expand out like it's not just going to simplify like the previous one did. And that's, again, if you think about your log laws and why that happened up here, because we could separate that out. We can't separate out this log. This isn't just log e of x plus a number. Okay, so we get something quite different here. So the derivative of log e of ax plus b is a over ax plus b. And again, that's just thinking about cover up your inside function, log e of something, derivative of log e of something is 1 on that something, and then multiplying by the derivative of that, which is a. And obviously that's where x is bigger than negative b on a, and that's just because that's the domain of log e of ax plus b. That's just about thinking about, well, I know ax plus b has to be bigger than 0, therefore ax has to be bigger than negative b, and therefore x has to be bigger than negative b on a in order for this whole thing to exist. Okay, finally, more generally, if we have log e of f of x, okay, so again, if you let u equal f of x, that means that you've got y equals log e of u, du dx is f dash x, derivative of f with respect to x, and dy du is again 1 on u, and this time u is f of x. And so that means that dy dx, which is dy du times du dx, is going to be 1 on f of x multiplied by f dash of x. So it's f dash x on f of x. And obviously that is where f of x is bigger than 0 in order to make sure that the log function is defined. Alright, so let's put our derivatives of logs into practice. Also thinking about potentially our chain rule, our product rule, our quotient rule, being able to differentiate polynomials, being able to differentiate exponentials. So differentiate each of the following with respect to x. So 2 times log e of 7x. So 2 times, remember it's a number times a function, so we don't need any product rule here. The derivative, when you've got a number times a function, the derivative of that will still just be that number times the derivative of that function. So dy dx is going to be 2 times the derivative of log e of 7x. Now if you use the chain rule, you're going to get 1 on 7x multiplied by 7, and the 7's cancel out. So remembering that log e of ax is just, the derivative of that is just 1 on x. So this is 2 on x. Wouldn't matter what number you put there, that derivative would still be 2 on x. Okay, the second one here, we've got dy dx. So you're going to need your chain rule here. Okay, we don't want to have to use let a equal every time. So I'm just going to get a sort of dark coloured highlighter. Okay, so let's imagine we're going to cover up our inside function. So we've got log e of something, log e of blue blob. Derivative of log e of blue blob is 1 on blue blob. Okay, so we get 1 on 3 minus 4x, but then we need to multiply by the derivative of 3 minus 4x, which is negative 4. So you get negative 4 on 3 minus 4x. There's a lot of negatives going around there. You might write that as 4 on 4x minus 3. It's the same thing. Okay, log e of 2x cubed minus 5x squared plus 1. Okay, so again, dy dx. Imagining covering up your inside function. You've got chain rule here. You've got a cubic inside a log. Covering up your inside function, you've got log e of something. Derivative of that is 1 on something. And then we also need to multiply by the derivative of the something, the derivative of the highlighted thing, and that is, in this case, 6x squared minus 10x. Now you must have brackets around that, or what you've written isn't correct, and then we can write that on our numerator, 6x squared minus 10x over 2x cubed minus 5x squared plus 1. You might choose to factorise the numerator as taking out 2x, so it'd be 2x times 3x minus 5, but there's no real advantage to doing that. Alright, I'm just going to move that over slightly, it's encroached on my next example. Okay, so the next one, we've got x times log e of 5x minus 1. Now this is really important, this is where you'll miss this. You've got a linear function times a log function. You need product rule, okay? So, we need product rule here, dy dx. We differentiate the first function, which is 1. Leave the second function as it is. Oops, log e of 5x plus 1. And then we add, and we leave the first function as it is, and we differentiate, multiply by the derivative of the second function. Derivative of log e of 5x plus 1 is 1 over 5x plus 1, sorry, not times 1, 5x plus 1, multiplied by the derivative of 5x plus 1, which is 5. Okay. So you're going to have log e of 5x plus 1 plus 5x on 5x plus 1. Again, those 5x's don't cancel, that's not how fractions work. You need common factors in the entire denominator, so a factor of the denominator and a factor of the numerator that can cancel. 5x is not a factor of the denominator. Okay, over here we've got log e of x on x squared, so we have a quotient of two functions, so we're going to use our quotient rule. So dy dx. Okay, we differentiate the numerator. Derivative of the numerator is 1 on x. We leave the denominator as it is, and we subtract, and we leave the numerator as it is, and we multiply by the derivative of the denominator, and then we have all of that over the denominator squared, which will give us x to the power of 4. Okay, so we've got 1 on x times x squared, so that's just x, minus, we've got 2x log e of x all over x to the 4. Now, we're actually not simplified here because we've actually got a common factor of x everywhere there. You can factor x out of the numerator, and that's important in this instance because it will cancel with the denominator. So that x will cancel with one of those, and you're going to have 1 minus 2 log e of x over x cubed. Okay, let's think about f. We've got quite a bit going on in f. So we've actually got this function inside a log function, so we're going to need chain rule. But this blue function I've just circled is also going to require chain rule because we've got that inside that, and that is going to require quotient rule. So we've got quite a lot going on here. So let's think about what's happening. If it helps you here to do a bit of let u equal the inside function to be able to deal with those derivatives separately, then absolutely do that. Okay. Alright, so what are we going to have here? We're going to have dy dx. Okay. It's equal to, so we've got log e of something. Okay. So log e of something is 1 over, I'm going to write that as 1 divided by here because it's a bit ugly, 1 divided by that something. Okay. And then we're going to need to multiply by the derivative of that something. Okay, now that something also requires a bit of chain rule happening here. So that something, oh sorry, let me change my highlighter colour this time. So this time we've got square root of that thing. Okay, so we might now think about what we've got here is 1 minus x on 1 plus x to the power of a half. Okay, so we're thinking about, alright, something to the power of a half. When we differentiate that, we get half times that something. Sorry, it's 1 minus x on the top to the negative half. And then we multiply by the derivative of that something. Okay, so now we're looking at differentiating this red highlighted section here. So that's going to require the quotient rule to do that. Okay, so quotient rule says we differentiate the numerator, which is going to leave us with -1, and we leave the denominator as it is, and we subtract, we leave the numerator as it is, and we multiply by the denominator, which is just 1. We do all that over denominator squared. Okay, let's tidy some things up here and see what we've got. Now, 1 divided by the square root of, okay, so you might think about that as being, okay, so this bit here alone is 1 minus x, 1 plus x to the half. If you do 1 divided by that, that's simply making that negative half. Okay, we might just write that like that because that's going to work quite nicely with the next part of the function. So this is going to be 1 minus x times 1 plus x to the power of negative a half. Okay, so then we've got multiplied by 1/2 and multiplied by 1 minus x, 1 plus x to the power of negative half again. Okay, so those are going to go together really nicely. This bit, and this bit. Okay, I'll come back to focusing on that last little bit in a minute. So if we think about those two things, we know when we're multiplying things with the same base, we add the powers, -1/2 times -1/2. So that's going to give us 1 minus x times 1 plus x to the power of -1. And then we've still got that half. Alright, and again I'll focus on this bit in a minute. And then this is going to be power of -1, just means we take the reciprocal. So I'll put that half out the front as well. So we've got half times, now it becomes 1 plus x over 1 minus x times. Okay, and now let's focus on this bit at the end here, and then we'll see what we've got. Okay, so this fraction here from the quotient rule, let's expand out that numerator. So we've got -1 minus x minus 1 plus x all over 1 plus x all squared. So the x's cancel out, so we've just got -2 over 1 plus x all squared. Alright, now actually, rather than keep my half here, my half is going to cancel with that -2, so we've just got -1 over 1 plus x all squared. Alright, so now let's put our fractions together. So we've got -1 plus x on the numerator over 1 minus x times 1 plus x all squared. And we've got a common factor of 1 plus x, so we can cancel that 1 plus x on the numerator with the 1 plus x on the one of the 1 plus x's on the denominator. So now we have -1 over 1 minus x, 1 plus x. And that denominator is a nice difference of 2 squares, so we could write that nice and neatly as -1 over 1 minus x squared. You've then got a lot of negatives, so you might choose to write that as 1 over x squared minus 1. So, simplifies quite nicely in the end. Okay, last example here. I think it's the last one. We want to have a look, as I said at the beginning, at what about if it's a log that doesn't have a base of e? So let's think about our change of base rule for logarithms, which we've looked at previously. If we have log base a of x, we can change the base to b by writing it as log base b of x over log base b of a. So let's make use of that change of base idea in order to find the derivative of log base 10 of x. So our rule for differentiating log is only for log base e. So let's focus on changing the base first. So to base e. So the derivative of log base 10 of x is going to be equal to the derivative of, now using this rule, we're going to have log e, we want to change the base to e. The thing inside the log goes onto the numerator, and the base of the log goes onto the denominator. So in this case, we're going to have log e of x on the numerator over log e of 10. Okay. Now, this does not require quotient rule because log e of 10 is a number. Okay. This is just a number, 1 on a number, times log e of x. You can take that out of the derivative. That's not doing anything. Okay. Sorry, that is the derivative of log e of x. Okay, so then we've got 1 on log e of 10 times the derivative of log e of x, which is 1 on x. And so our answer is 1 on x times log e of 10. And obviously we could generalize that to any base. So if we were differentiating, log base a of x, the same logic would apply. We change the base and ultimately we'd get 1 on x times log e of a. Okay. But again, you don't need to know that rule, but just that sense that our rule is only for log base e. It's possible to differentiate other bases of logs by first changing them to logs with base of e. Okay, so work today is again from a worksheet, this time found in Appendix G of your booklet.